Random vibrations are widely used in engineering to evaluate structural response under unpredictable loads. Hello, I'm Armin. Welcome to my channel. In this video, I'll perform a random vibration analysis on a 4-deck rack and calculate the stress, displacement, and fatigue life based on 1, 2, and 3 sigma criteria. Before we start modeling, let's briefly go over the setup.
Random vibration refers to motion or excitation that cannot be predicted precisely because it is stochastic. In simple terms, it shows irregular and broadband energy that changes over time. Engineers describe this behavior using power spectral density, PSD, which shows how vibration energy spreads across frequencies. In practice, random vibration analysis is vital when structures or systems face unpredictable loads, such as road roughness, ocean waves, or wind. Since these excitations are uncertain, engineers analyze the response probabilistically, using measures like RMS displacement and stress variance instead of single deterministic values. When a structure or component is exposed to random excitation, such as rough terrain or seismic motion, it vibrates in an unpredictable way. Engineers mainly focus on displacement, velocity, and stress, which in most cases are assumed to follow a Gaussian or normal distribution. In this distribution, sigma, or standard deviation, represents how much the response varies around its mean. The root mean square value, RMS, corresponds to 1 sigma. By evaluating responses at 1, 2, and 3 sigma levels, engineers can estimate typical vibration amplitudes and rare extreme conditions, ensuring safe and reliable designs. The Gaussian distribution is bell-shaped and symmetric around the mean, which in vibration problems is usually 0, since motion oscillates equally in both directions. Most responses stay near this mean, while only a few reach the extremes, where sigma, or standard deviation, becomes crucial. 1 sigma covers about 68% of all responses, representing the typical vibration amplitude, or normal operating range. 2 sigma includes about 95%, capturing moderate peaks that remain within safe limits. 3 sigma covers roughly 99.7%, representing rare and extreme peaks, the maximum expected displacements or stresses that are unlikely to occur but are vital for safe design. In this tutorial, we'll investigate a rack structure consisting of 4 decks, with a thickness of 2 mm for the decks and 3 mm for the bracings. Since random vibration is a linear analysis, we first need to perform a modal analysis to calculate the mode shapes, which will then be used for mode superposition in the random vibration analysis. The material is structural steel, and I'll create the geometry in SpaceClaim using shared topology to connect all parts together. For the modal analysis, the boundary condition is a fixed support at the base of the bracings, and the number of mode shapes is set to 20. The random vibration system is coupled with the modal analysis and uses a PSD G acceleration applied to the fixed support with a reasonable input profile. After solving, we can extract the results. We'll investigate the stress and displacement of the rack under 1, 2, and 3 sigma criteria. Then we'll examine the response PSD of the displacement in the x direction, where the acceleration is applied. The maximum displacement occurs at the 5th mode because the rack primarily moves in the x direction. Finally, we'll analyze the fatigue life of the rack. The results show that the rack would completely fail after about 5,943 seconds of exposure. That's enough explanation. Let's start modeling. Random vibration analysis is a linear type of analysis, so before performing it, we first need to add a modal system. To do that, double-click on Modal. In the first step, I'm going to create the geometry. I'll right-click on Geometry and select New SpaceClaim Geometry. Now, let's start by drawing the decks. The default work plane is set to the XZ plane. From the Sketch tab, I'll choose Rectangle and click on Plan View. I'll start the rectangle from the origin point and type 300 millimeters in the Z direction and 900 millimeters in the X direction. You can switch between the dimension fields using the Tab key. Finally, press Enter to complete the rectangle. Then, click on End Sketch Editing to finish the sketch. Now we have a rectangle. Next, I'd like to add fillets to the corners of the deck. I'll click on one corner, hold down the Control key, and select all the corners. Press and hold the left mouse button, drag it downward, type 5.5 millimeters, and press Enter. After that, press Escape. And there we go. 4 rounded corners have been created. Let's check the fillet radius to make sure everything is correct. I'll press Escape, go to the Measure tab, and select the Measure tool. Then I'll click on one of the corners. As you can see, the arc radius is 5.5 millimeters, which confirms it's correct. In the structure tree, we can see a surface representing the deck. If I click on it, the Properties section appears, where I can specify the thickness. I'll enter a deck thickness of 2 millimeters and press Enter. On the right side of the surface name, we can now see 2 millimeters displayed. Next, let's add 4 decks for the rack. I'll select the deck, go to the Design tab, and click on Move. Holding Control, I'll drag the coordinate in the Y direction, type 175 millimeters, and press Enter. Now we have 2 decks. I'll repeat this process to create 2 more trays. Click on the second deck, hold Control, drag it, and type 200. We need 1 more, so I'll repeat the same steps again. Finally, press Escape. Now we have 4 different decks, but one of them is on the ground, so we'll delete that deck. Select that deck and press the Delete key. Then, to add another tray at the top, use the Move tool again. Hold Control, drag upward, type 200, and press Enter. Everything looks good now. Next, we're going to create the rack bracings. Let's get started. I'll begin by hiding all the decks and keeping only the first one visible. Then I'll click on it, switch to Sketch mode, and select Plan View. Now we have a clear top view to work with. From the Sketch tab, I'll choose the Line tool. I'll click on the tangent point of the arc and draw a vertical line of 46 millimeters. Then I'll press Escape. Next, I'll click again on the tangent point of the arc and draw a horizontal line of 31 millimeters, then press Enter. Now I'll go back to the Sketch tab and choose the Tangent Arc tool. I'll select the 2 endpoints of the lines to create the connecting arc. Everything looks good so far. Before clicking on End Sketch Editing, I'll hide the surface because the bracing should not merge with it. You can notice that a curve folder has been added in the structure tree. I'll double-click on the curve to select all segments. Then, with the left mouse button, I'll click, hold, and drag downward. I'll type 775 millimeters and press Enter. And there we go, the bracing has been created. I'll press the Escape key and show all the decks again. Each deck has 4 bracings, so I'm going to use the Mirror tool to create the remaining 3. To do that, I need to add 2 planes in the middle of the decks, which we'll use as mirror references. I'll go to the Design tab and select Plane. Then I'll click along the X direction and the Z direction and press Escape. Now 2 planes are ready. Next, I'll select the first plane,
press the M key to activate the Move tool, select the X direction, and type 450 millimeters and press Enter. After that, I'll click on the second plane, drag it in the Z direction, type 150 millimeters, and press Enter. Finally, I'll press Escape. The planes are now positioned and ready for the mirroring process. Now I'll select the Mirror tool from the Design tab. I'll choose the first plane as the mirror plane and select the bracings as the object to mirror. Now we have two bracings. Next, I'll click on Select Mirror Plane again, choose the second plane, and select both existing bracings. Now, 4 bracings have been created. I'll double-press Escape to exit the tool. Since we no longer need the planes, I'll hide them. Next, I want to specify the thickness for the bracings. Similar to the deck, I'll select All Bracings. In the Properties window, I'll enter a thickness of 3 millimeters for all of them. Everything looks good so far. The bracings are bonded to the decks, so we can either use shared topology or a bonded connection. I'll use the first option. I'll switch to the Workbench tab and click on Shared Topology. As you can see, 48 edges have been detected. I'll click on the green check mark to confirm. Now the geometry is complete. Press Escape, save the model, and close SpaceClaim. The material is selected as structural steel by default, so I'll leave it as it is. Now I'll double-click on the Model cell to open ANSYS Mechanical. We're now inside ANSYS Mechanical. As you can see, there aren't any connection definitions between the parts because we used shared topology in SpaceClaim. If we hadn't used shared topology, bonded connections would have been created automatically. Next, let's adjust the mesh. Click on Mesh, and in the Element Size field, you can see that the default value is around 20 millimeters. I'm going to change it. Click on it, type 10 millimeters, and press Enter. Now right-click on Mesh and select Generate Mesh. The mesh has been generated. As you can see, the mesh pattern is structured. In the Statistics section, we can see the number of elements. It's a little over 13,000. Now it's time to define the boundary conditions. Right-click on the Model node, go to Insert, and select Fixed Support. Double-click on the bottom of the base to select all lines, then click Apply. Let's add the fixed supports for the other bases as well. Double-click on the next base, click the plus icon, and repeat this process for the third and fourth bases. Now all 4 bases have fixed support boundary conditions. Next, let's specify the number of mode shapes to extract. In the Analysis settings, we can specify the number of mode shapes we want to extract. The default number is 6, but I'll change it to 20. Type 20 and press Enter. Now we can solve the model to find the first 20 natural frequencies. Right-click on the model and select Solve, or you can also click on Solve from the Environment tab. The solution is now complete. Click on Solution, and you can see the natural frequencies listed in the tabular data. The maximum natural frequency is around 68 Hz, and the first one is about 12 Hz. In linear random vibration analysis, ANSYS uses the mode superposition method to calculate displacements. So it's important to ensure that the maximum frequency from the power spectral density, or PSD, is within about 1.5 to 2 times lower than the highest natural frequency. For example, since our maximum natural frequency is around 68 Hz, we can set the PSD frequency range up to about 45 Hz in the random vibration setup. Now let's check the mode shapes. I'll click on the edge of the tabular data, right-click on Modes, and select Create Mode Shape Results. Then right-click on Solution and choose Evaluate All Results. Now we can see the mode shapes and their corresponding natural frequencies. For better visualization, let's hide the mesh edges. Go to the Results tab, and from the Edges section, select No Wireframe. Now the deformation patterns are clearer. As you can see, some of the modes appear repetitive. That's because the model is symmetric and all decks are identical. The modal analysis is now complete. We can close the model and proceed to the next step. It's time to set up the random vibration system. I'll click on Random Vibration, drag it, and drop it into the Solution cell. As you can see, the results from the modal analysis are automatically imported into the solution of the random vibration system. Now I'll double-click on Setup. The geometry, engineering data, and boundary conditions are also imported from the modal analysis into the random vibration analysis. We're now in ANSYS Mechanical. As you can see, the modal results need to be updated before proceeding. So I'll right-click on Model and select Solve. The modal solution is now complete. Next, I'll return to the random vibration system. As you can see, the modal branch is now added below the random vibration system. Now we need to specify an excitation source at the base of the bracings. I'll right-click on Random Vibration, and from the Insert menu, we can define acceleration, velocity, or displacement as the input. In this example, I'll select PSD acceleration, defined with respect to gravity. For the boundary condition, I'll select the fixed support. Since we only have one fixed support in this model, it automatically applies to all base supports. This type of simulation represents a base excitation, so the acceleration is applied to the fixed boundary condition, which is connected to the ground. Next, let's specify the frequency and acceleration values in the tabular data. I'll start with 5 Hz and enter a PSD value of 0.01. After pressing Enter, we move to the next row. Then I'll type 15 Hz and 0.015, followed by 20 Hz and 0.017. Next, I'll enter 25 Hz. Note that the PSD values must vary gradually. If you enter a sudden or unrealistic change, the software will warn you. For example, if I type 1, the line turns yellow, and if I enter a very large value, such as 100 or more, it turns red, indicating that the profile is incorrect. Therefore, the PSD variation must remain reasonable. I'll continue entering the remaining frequency and PSD values to complete the table. This profile looks suitable for our simulation. Remember, these values depend on your excitation force and frequency interval. In the Direction section, we need to specify the direction of acceleration. I'll select the x-axis so the acceleration will be applied in that direction. Everything looks good so far. Now I'll right-click on Random Vibration and select Solve. Then, wait for the solution to complete. Solution is complete. Let's check the deformation results. I'll right-click on Solution, go to Insert, and select Directional Deformation. The orientation is set to the x-axis, and the scale factor is 1 sigma. Now I'll duplicate it without results and change 1 sigma to 2 sigma. Then I'll duplicate it again and change 2 sigma to 3 sigma. Next, I'll right-click on Solution and select Evaluate All Results.
Here you are, we can see the directional deformation in the x-axis with 1, 2, and 3 sigma criteria. Note that we can't see the animation of the deformation because random vibration is statistically inherent. Now let's look at the stress distribution in the structure. I'll right-click on Solution, go to Insert, and select Equivalent von Mises Stress. Then I'll duplicate it, change 1 sigma to 2 sigma, and duplicate it again to set 3 sigma. Finally, I'll right-click on Solution and select Evaluate All Results. Here you are, we can see the stress results in the structure. For example, 3 sigma means the maximum stress with a probability of 99.73% is below 314 megapascals. And 2 sigma means the maximum stress with a probability of 95.54% is below 209 megapascals. We can also see the directional deformation results. In the x-axis, the deformation is 6.47 millimeters with a 95.45% probability that it remains below this value. Next, let's look at the response PSD. I'll right-click on Solution, go to Response PSD, and select it. After expanding Response PSD Tool folder, we can see the Response PSD. I'll choose the Vertex filter, select the edge of the upper deck, and click Apply. Now I want to see the displacement in the x-axis. In the reference section, the absolute option is selected, meaning the base motion is included, so the entire base moves in the x direction due to the base excitation. Let's duplicate the result, change the reference to relative, and then right-click on Response and select Evaluate All Results. Here you are, we can see the displacement versus frequency in the x direction. The maximum displacement occurs at 23.3 Hz, which corresponds to the 5th mode shape. At this frequency, the rack is moving primarily in the x direction. If we compare the results again, we can see that the absolute displacement is larger than the relative displacement, because the relative result considers only the rack motion, excluding the base excitation. Now let's investigate fatigue behavior. I'll right-click on Solution, go to Fatigue, and select Fatigue Tools. Then I'll right-click on it, go to Insert, and select Life. You'll notice a question mark next to life because we can't calculate it without velocity and acceleration data. So I'll click on Analysis Settings, go to Output Controls, and change No to Yes for both velocity and acceleration. Now I'll right-click on Random Vibration and select Solve again. Once the solution is complete, you'll see a green check mark next to life. Let's click on life to view the result. We can see the life of the rack structure measured in seconds. This means if the structure is exposed for 59.43 seconds, it will experience 100% failure. Note that the fatigue tools use Steinberg theory, which is widely used for electronic components and small structures. The exposure duration is set to 1 second by default. This value doesn't change the life, but it does affect the damage calculation. Now I'll right-click on Fatigue Tools again, select Damage, and update the results. As you can see, the maximum damage appears around the bracing area. It's a good idea to enable the maximum probe to easily locate the highest damage point. In the life result, the minimum life is about 5,943 seconds. If I change the exposure time to match this minimum life value and update again, you'll see that the damage becomes 100% or 1 because damage is the inverse of life, and the life remains unchanged. That's all for this tutorial. Thank you for watching, and if you found it helpful, please like the video and subscribe for more ANSYS tutorials.